Hello everyone, and welcome to another video of my series on calculus. Today we are going to do a very quick review of functions and kind of what they are and cases where they might not be really well defined. And we're also going to talk a little bit about some of the different types of functions that we're going to see. Piecewise functions, for example. I know a lot of you have probably already studied this in your math courses, so even if you might have seen this material before, I still do think it might be a good idea to kind of go over these review videos just to brush up on the basics. Honestly, a lot of the times when we are just doing the math, we kind of take the basics for granted, so we might have forgotten some of the more fundamental information, such as what really defines a function. But again, if you do truly feel like you already know all of this, then feel free to skip over it. And we're going to start to get to the actual calculus in a couple episodes. I don't know how many it's going to take, but it shouldn't take too long. So, when we think about functions, there's a couple of ways that we can represent them. And really the most abstract way to define a function is that it is any process which takes some input and gives us an output. The most familiar way that you see this is probably in equations. For example, you are most likely familiar with the equation for the area of a circle. A is equal to pi r squared. What is our input for this equation? Well, our input is going to be the radius of our circle, and the output that we get for that input is the area. Pretty self-explanatory. Notice how we are given a specific form. We know exactly what our output is going to be given the input that we have, and we're able to calculate it every single time. Now here is another example of what we might consider a function. Yes, it is still a function even though it is in a different form of our equation. And I want you to notice a couple of things. For one, we have an input and we have an output, which is exactly what a function is. But notice that all of our inputs are integers. We have for our input the specific year, which we are counting the population for. Compare this to our previous representation. Here, our radius of the circle doesn't necessarily have to be an integer. It could be a fraction, it could be a decimal, it could be really any positive number. Compare that to here, we can't really have a fraction of a year. It wouldn't really make sense to take a poll of what the population is in the middle of the year or a tenth of the way into the year. It just doesn't make a lot of sense logistically. So we restrict ourselves to integers. Furthermore, we don't have some equation. We don't have some defined form that will let us calculate the population for any year that we want. The best we can really do is kind of plot these years on a graph and draw a line between the years to kind of have an estimation for what the population might be in between these data points. But again, that's really an approximation at best. There is no really equation that will tell us what the population will be for any point in time. There's too many variables. What if there was a war? What if there is a reduction in the birthing rates? It's just too many factors at play. So after looking at these two examples, we are ready to formally define what a function really is. A function f is a rule that assigns to each element. I'm going to go a little bit more into what exactly an element can be in just a moment. In a set D exactly one element, excuse my terrible handwriting, called f of x in a set E. Now you might be asking yourself, what is a set? What is a element? Well, a set can be simply thought of as a group of objects. You can think of it kind of like a box. A set is a box, and anything that we put into that box is a part of that set. So what can we put into a set? Well, we can really put anything. We don't have to just constrict ourselves to numbers. Let's look at the two examples here. Here, for our equation of a circle, we can think of our input as a set. Our input is a box of numbers which we can plug in as our value of r. Well, what values can we plug into this equation? Technically, this can be negative because r squared is always going to be a positive number. Whether it's negative or positive, the final result is always going to be positive. However, when we think about the radius of a circle, we don't typically describe it as being negative. In that sense, within the context of this problem, because we're talking about a circle, we restrict ourselves to only positive values because that's just how we measure the radius. We measure the radius as a positive value. So our input, which is a set of numbers that we can put in, is restricted to being just positive values. And again, our output is the same. These are two different sets. We have a different set for our input. So we have a different set of numbers that we can use for our radius. And then our output is a completely separate set, which is the set of numbers that we can get for the area of a circle. And again here, the year is our input. So this is some sets. In this example, we can think of this as set D, which is our input. And then we have our set E here, which is our population. So looking at this definition, our function takes an element in our set D, which is our input, and in this case, our element is the year, which we are taking the population for, and it assigns a value called f of x in a set E. And here is our set E, where each population is an output value that we assign to each input value, which is the year. Typically, when we have a set of our inputs, we call that set our domain. Our domain is the range of numbers that we can use as our input. And then when we have our output, which in this case would be the population, we call the output value the range of the function. So the domain of our function is the set of values that we can use as our input, and the range of our function is the set of outputs that we assign to each of those inputs. Now I want you to notice something. In my definition of a function here, I specifically said that in our set we have an element. An element doesn't have to be a number. An element can be anything. An element can be an action that we are performing. An element could be a name that we are assigning to some other elements. Maybe that other element is a person. Really, our element can be anything. So when we are working with math, 95% of the time, we are working with numbers. But I want to emphasize that we don't have to work with just numbers. For example, if you ever start coding, which you probably are going to do eventually, when you code, when you program, you define functions. And in those functions, you are going to define an input and an output. Now, those input and outputs don't necessarily have to be numbers. For example, when you went to my channel and you clicked on this video, The input that you performed was you clicking on this specific video, and what was the output? The output was that you were directed to this link, which is where the video is stored. Notice our input and our output aren't necessarily numbers, they're actions. The input was the mouse click that led to you, the output, being directed to this video. That really is one of the biggest strengths of math. It's so arbitrary. We don't have to constrict ourselves to anything. Now, because we're studying calculus, we are going to most of the time be focused on numbers because, well, that's just the field that we're studying. But if you're ever going to take a CS class, you're going to be working in a much more general sense, in a much more general context, where you're going to be defining functions which don't necessarily just take numbers as their input and output. Now, going back to our equation for a circle, there's a couple of other terms that I want to make sure you guys are familiar with. Our input, which is the radius of the circle, is considered an independent variable. We can replace this variable r with any value that we want as long as it is defined in our domain. So when I say independent, you can think of this value as being independent of every other value, which means that the only thing that affects the value of r is us. We are the ones who choose whatever value we want for r. In contrast, the area is our dependence variable. The area of our circle depends on the radius of it. All right? Area depends on the radius. Therefore, this is the independent variable, our input, and this is the dependent variable, our output. Now, you've probably seen a couple different visual representations of what a function is, and this is probably one that you're really familiar with. This is when we define the function as a machine. So we have some independent variable, x, which is defined in our domain, and we put it through some machine. And this machine, it manipulates our independent variable in some way. In this example, what it's doing is it takes an independent variable, it squares it, and then it multiplies it by a factor of pi. And that gives us our area, which is our value of f of x. Now, again, as we described before, we won't always have an equation for a process. We won't always know what is going on inside of this machine. Sometimes we're just given an independent variable and then we are given an output. In the example where we are looking at the population, we don't know what's going on inside of here. That's not necessarily a bad thing. We won't know what's going on inside of the machine a lot of times. Even when we do have some equation, it really is just an approximation at best. This is assuming ideal circumstances. This is assuming that we have a perfect circle. We are not always going to have a perfect circle. In those cases where we don't have a perfect circle, this is just an approximation. A good one, but an approximation nonetheless. Now, I'm going to go over another visual representation that you've probably seen before. And this is a good way of kind of understanding the concept of a set and what is really going on when we made this very formal definition of what a function really is. So, recall that a function takes some elements in our set D here, and then it assigns to that element in our set D, which can be X or A or B. These are elements in our set. And this function takes one of those elements, wrong color. It takes one of those elements and it assigns it a specific value. In this case, we're going to call the value that is assigned to X, f of X. Say we take the element A. It's in our set D. It goes through the function. It assigns it a value, which we call f of A. Set B takes it, assigns a value to it, f of B. This is the exact thing that happens in every function. This is the exact process that's followed. And this set right here, which is our set of outputs that we assign to each of our inputs, it is set E. Okay? Hopefully that kind of makes the concept of sets and assigning an element in those sets, a value in a separate set, a little bit more approachable. But one of the most useful representations of a function is a graph. What is a graph? I'm going to introduce some new notation to you guys here, and I'm going to try to kind of explain what exactly this means, because you may or may not have ever seen this before. So a graph is just a set of numbers, x, f of x, such that x is in our domain, which we are going to call D. So this is our definition of a graph, and pretty much what it's saying is, okay, a graph is a set of points, x and f of x, such that x is a part of our domain. So whenever you see these brackets in a math class, it is defining a new set. So everything that is inside of these brackets is a set. Now, you might be looking at this line and kind of wondering what it really means. This vertical line here, it's a notation that you're going to see in a lot of math classes. And pretty much what it does is it's constricting this set of values to be within this set. X and f of x at this point can really be anything. X can be a real number, x can be an integer, x can be an imaginary number, it can be whatever. What this line is saying is that this pair of numbers, x and f of x, is only going to be defined if x is in our domain. This is important because we want x to be in our domain. We don't want x to be outside of our domain. For example, I mentioned beforehand that we only want to take integer values for our year in our table. So that means that our domain is only going to consist of integer values. We don't want to take any values that are outside of that domain. We don't want to take any imaginary numbers. We don't want to take any fractions. Those are outside of our domain. We don't want to take negative numbers for our value of the radius because a negative radius does not make sense. It is outside of our domain. We want to ignore those. So pretty much that's what this notation is doing. So then we have kind of our formal definition of what a graph is. Now we can apply that definition to see what it looks like visually. Let's say for this graph that we assign x is equal to 0 to be 1. I'm just going to draw a random function here. It's not too important what exactly it represents. Pretty much what you see here is that any arbitrary value x has some value f of x assigned to it. And this point right here can be described as a pair of numbers, x and f of x. Now, the reason why the graph is such a useful representation of a function is because we can see a lot of things that might be difficult to see in an equation or in a table. For example, we can see the range of values that our output has. I'm just going to assign a random number to this. I'm just going to say that the maximum output that our function can have is 6, whatever. And then our minimum output that our function can have, which is like right here, is -3. We can see a visual representation of what values our output can take. We can also see a visual representation of what values our input can take. Our function only takes values from x is equal to 0 and x is equal to, let's say, 9. All right, I know this is super messy, but hopefully you get the point. This is our domain. All right, this is our range. Graphs are a very good way of finding these values. Graphs are a really good way of finding the range of a function, the domain of a function, because it's so visually easy to see. It wouldn't be as easy to see what the range of our population would be if we looked at a table. It wouldn't be as easy if we just looked at an equation. Here I made a little graph that corresponds to the table that we had worked with earlier. So you can see here that I just took the independent variables and I plotted the output for those independent variables on this graph. It's not exactly to scale. I didn't really try to make it exactly to scale. I just really did this to show you why it might be useful to switch between some of the representations that we talked about earlier. So one benefit of switching from a table to a graph over to a graph is that we can see somewhat of a trend, right? We can see this trend where it's almost like a parabola. At first, the population is slightly increasing, but then it starts to increase faster and faster with each decade. Now, I already mentioned before that we can't find an exact equation for the population of the Earth, which is still true. However, we can find something that is called the line of best fit. And pretty much what that is it's an approximation. So, no, it's not an exact equation, but kind of looking at this graph, we can tell that there's a general trend where the line kind of starts off here and it keeps going up and up, kind of like that. Something like that. The line doesn't go through all of the points, but it does get really, really close to them. Now, this is just something that I kind of just drew by eye, but there are better methods, more analytical methods for finding lines like this, for finding a line of best fit. Something that we're going to talk about a bit later is taking a table of values, plotting them, and then finding some line that kind of corresponds to an approximate trend that we might see. That way, we have a general sense of the trend, even if it might not be exact. And this is something that you're actually going to have to get used to. Whenever we do real-world experiments, there's always some sort of error, all right? Whether it might be human error or measuring errors or error with the machine, there's always some sort of error. We're never going to have an exact pattern on a scatter plot that we can look at and find some equation that perfectly models that pattern and goes through each of those points. It's not possible. That's why it's so important to take a table of measurements, plot them on a graph, and kind of approximate what the trend is. So now that we've kind of discussed what a function is, we should also discuss what a function isn't, because there are models which you might encounter which can't be classified as functions. And it's important that we can tell the difference between what is one and what isn't one, because if we can immediately tell if a model isn't a function, that rules out already a lot of the approaches that we can take with the problem. Here I have a new table, and I want you to look at this table and tell me why it's not a function. Recall what our definition of a function is. It is a rule that assigns to each element in a set D exactly one element in a separate set. So what about this table goes against that definition? Take a moment and think about it. The reason why this table doesn't define a function is because here we have two input values that are assigned to two separate output values. In our definition of a function, we specifically stated that each input is assigned to exactly one output, not more than one output, just one output. That means that whenever we have the same input into our function, we should be getting the exact same output. We can't have some input value that is assigned to multiple output values. Think back to my example about clicking a link on some website. Imagine you click the link and it directs you to this video. Now imagine at a later time that you click that same link again and then it directs you to Amazon. That link is a broken link. That link does not define a function. A function should have a consistent output every time we have the same input. Otherwise, it doesn't make sense. Now, there's something that I should point out. This rule does not work in the reverse direction. What do I mean by that? Well, notice that we have two separate inputs, x is equal to 4 and x is equal to 5, that give us the same output, 8. This is fine. As long as the inputs are separate, they can be assigned to the same function value. It doesn't matter if it's 2 inputs, it doesn't matter if it's 3, we can have an infinite amount of inputs that are mapped to the same value. This does not go against the definition of what a function is. Now, I think another really good way of thinking about it is kind of thinking about a guitar. And don't worry, I'm not gonna burst into this song or anything. I'm not gonna pull Colleen Ballinger. This is not that kind of video. I do think it's a really great way to kind of think about functions and how their inputs and outputs are mapped. So if I, for example, struck this high E string, it gives me one note. And every time that I pluck it, it gives me the same exact note. I don't want to start plucking the string and then in the middle of me plucking it, the note changes. That would be an example of having some input that I keep on putting into this function. And then out of nowhere, I get some output that is different from the rest. I want my notes to be consistent. If I pluck the same string, I want one note to ring out each time. Now, I know you can't really see it with this camera angle. I can't really find a way to show it to you that well. But the way that a guitar is tuned, I can actually play the same note in 2 separate positions. These are not the same string. I am playing 2 separate strings right now, and yet I'm able to play the same note because of the way that it's tuned. This is an example of where I have 2 different inputs that give me the same output. So, thinking about the positions that my finger are on the fretboard and the note that I get when I pluck the string, that describes a function. So with that knowledge, we can look at a table like this and tell that it's not a function. But let's apply the same idea to a graph. Looking at this graph, how would we be able to tell whether or not it's a function? Well, you've probably seen this before. It's called the vertical line test. The way that you can tell if some input in our graph is mapped to multiple different outputs would be if there was more than one point along some vertical axis. So here, pretty much this vertical axis is at x, and we see that there is only one point defined at x. This is what we want. If there was some other point that was defined here, or maybe here, anywhere along this vertical line, that would go against our definition of what a function is. Now, this would be an example of something that doesn't model a function. You see here that we have multiple points along our x-axis that have more than one output assigned to them. The reason why you never see graphs like this in a math class is because they don't describe what a function is. 99% of the time, when you see a graph, it's going to pass this vertical line test. If it doesn't, then a lot of the rules which we use in math don't apply to that model. Now, I'm going to introduce a new concept called a piecewise function, and I'm going to introduce it through an example. So if we have some function f of x, but the domain of this function is split into 2 different pieces, kind of like 2 different puzzle pieces that you put together. So we have one part of the domain where the function is defined as 1 minus x, and this is only valid if x is less than or equal to -1. And then the other part of our domain is equal to x squared. And this is only true if x is greater than -1. Notice that this does not go against our definition of what a function is. The reason why it doesn't go against it is because of this less than or equal to sign. If both of these functions here were defined at x is equal to -1, this would not be a function anymore. But because this one is equal to -1 and this one is only greater than -1, we do have a function. So again, you can see that the domain is kind of split up into these two separate parts where different functions are defined. And you know, if you were to plot this, it would be very similar to kind of putting two different pieces of a puzzle together, but they exist on the same domain in a sense. That domain is just split into two different groups. So if I was to look at this function and ask myself, okay, what is the value of this function at x is equal to -2? Well, let's look at that. F of -2. If x is equal to -2, which part of the domain does that value fall under? Well, x is less than -1. -2 is less than -1, which means that this is our defined function for that domain. So then here, this would be equal to 1 minus -2, and the answer to that is just 3. Again, looking at a different value of x, let's say we look at -1. Well, here, just like I mentioned before, this domain does not include -1. This domain only includes x values that are greater than 1. So this is not the function that we use. This is the function that we use, because here the domain is less than or equal to -1. So this would be f of x is equal to 1 minus -x, or what am I doing? 1 minus -1, which is just equal to 2. And then for our last example, we can say what is the value at x is equal to 0. 0 is greater than -1, so we use the bottom function. This is equal to 0 squared, which is just equal to 0. Pretty simple. So we see what the equation looks like. What does the graph of this function look like? So for x is less than or equal to -1, we have 1 minus x, which is pretty much just the equation of a straight line. So -x is our slope and 1 is our y-intercept. So if we define 1 to be like around here, then we know that this graph, 1 minus x, must go through 1. But it actually doesn't ever go through 1, because by the time that it reaches that f of x value, it is no longer defined over that domain. So it actually stops around here, -1. That's kind of like the point where our domain is split. And we already know what the value at x is equal to -1 is going to be. We already solved for it. It's just going to be equal to 2. So here, if this is 1, then 2 f of x is equal to 2 would probably be around here. And this would be the point defined in our function. And the slope is just -1. So it would look something like that. And if you don't exactly remember how to draw a graph for a variety of functions, don't worry too much. I am going to kind of do a refresher on that in the next video. So if you don't remember everything, we will be going over that very briefly. So here, this is our cutoff point, and we defined the function for x is less than or equal to -1. What about x is greater than -1? Well, here, f of x is equal to x squared. So we know that x squared is 0, x is equal to 0. However, x squared isn't defined at x is equal to -1, but we can still plot it. What we do is we draw this as an empty circle. Notice here how I specifically drew this as a filled-in circle and this as an empty circle. What this means is that at this point, x is equal to -1, this part of the graph is defined. The graph is not defined at this point. If you ever see a empty circle, that means that that point the function is not defined. And then we can kind of follow the rest of the trend of what a parabola looks like, something like that. So that's kind of our graph of what this piecewise function looks like. So you can see here that at this point where the domain splits, our function kind of shifts. It jumps. There's this gap in between them. That's okay. This can still be defined as a function. Now, one of the reasons why I wanted to talk about piecewise functions is because there's a very important function that we are going to use throughout this course that is a piecewise function, and that is the absolute value function. This function just describes the distance that our value x is from 0 on a number line. That's it. It's that simple. So if we have some number line, some real number line that kind of goes like this, and then we have our 0 point here, and I'm just going to fill out the rest of these. So here we have our number line, and it's going to kind of help us visualize the absolute value. So if we wanted to find the absolute value of 3, for example, all you have to ask yourself is how far is 3 from 0 on the real number line? Well, 3 is located right over here. And we know that this is 0. So then the distance between 0 and 3 will be represented by this bar. What is this equal to? Well, it's pretty simple, right? We have 1, 2, 3 steps, so this is just equal to 3. Another way you can think about it is just taking the difference. 3 minus 0 is equal to 3. Now, what if I was to ask you what the absolute value of -3 would be? What would that value be? Well, -3 is right here. So what would this bar be equal to? The thing about distance is that it is always going to be positive. That is the definition of a distance. A distance is a scalar, which is a number that doesn't have any direction. You can't have a negative distance. So in this case, the absolute value of -3 is not equal to -3. It's actually equal to 3 again. This makes sense because whenever we have some positive number, the negative of that number is going to be the same distance away from 0 as the positive is going to be. These two points, 3 and -3, are symmetric about 0. This 0 is the middle point. It separates the numbers exactly at the middle. So the distance from 0 to 3 and 0 to -3 is going to be the same. Let's now look at another number. Let's look at the absolute value, the square root of 2 minus 1. What is this equal to? Well, the first thing that we should ask ourselves is this a negative number or a positive number? If it's a negative number, then the absolute value is not going to be equal to root 2 minus 1. If it's a positive number, then it is. Root 2 minus 1 is a positive value, and it's going to fall around right here, I would say. So the distance between these 2 points, represented by this graph, is just equal to root 2 minus 1. Whenever we have a positive value and we're trying to find the distance from 0, it's just always going to be equal to the value. Now for the final example, we're going to look at the absolute value of 3 minus pi. Recall what the value of pi is. You don't need to know the exact value. It's about 3.14, yada yada yada, whatever. The point is that pi is greater than 3. That means that this is not going to be equal to 3 minus pi. It's not, because it's not a positive value. 3 minus pi is going to fall around right over here on this real line. Not an exact point, doesn't matter though. So we know that this is a negative number and we can't represent distance with a negative number. The distance isn't equal to this negative value, but it is equal to its positive counterpart. So if we just take the negative of 3 minus pi, then we will get pi minus 3, which falls somewhere around here. This is super messy. I'm going to kind of separate these two. Pi minus 3 is the positive counterpart to 3 minus pi. These two are the same exact distance away from the 0. So then, we know that 3 minus pi, the absolute value of that, is equal to pi minus 3. So after looking at all these examples, we can write a algebraic form for the absolute value function. Absolute value of x is equal to x if x is greater than or equal to 0, and negative x if x is less than 0. And you can interpret this by looking at the real line. It's pretty much saying if our x is to the right of 0 on our real line, then the absolute value is going to be equal to the value itself. If it is to the left of our real line, then it is going to be equal to the negative of the value. And now that we have a function algebraically, we can draw the graph. So here, the point where our domain is split is at x equals 0, and we know that for x greater than 0, it's equal to x, so it's going to look something like that. And for the left part of the domain, x is less than 0, it's equal to negative x. The slope is the same, but it's just going downwards, so it's going to look something like that. So really, whenever you see the absolute value function, it's just representing distance from 0. That's it. It's that simple. Don't make it any more complicated than that. Functions have certain properties. We're going to look at those properties a lot as we progress through the course, but for now we're just going to focus on two important ones. So a function can be classified as even if f of negative x is equal, f of negative x, this is a negative sign, if you couldn't tell, is equal to f of x. We can see that over here in our absolute value function. Here we have x is equal to 3, and we have a function value that is assigned to that x. But if we look at x is equal to negative 3, it's a different input, and yet it gives us the same output. So this is an even function. If we have two independent variables, x and negative x, which give us the same output, that function can be classified as even. The counterpart to an even function is an odd function. Function can be classified as odd if f of negative x is equal to negative f of x. In this case, for the even function, we have two different inputs that give us the same output. Whereas here, we have two different inputs, and one of them gives us the negative output of the other. Let's look at that graphically. So we already saw what an even function would look like. Let's see what an odd function might look like. So here we have some x here as our input, and we have some output, f of x. If we look at negative x here, we see that the output of negative x is not equal to f of x, but it is equal to the negative of f of x. Here, these are symmetric, just like how an even function is symmetric. An even function is symmetric, but an odd function is symmetric as well. They just have different symmetries. If we take this portion of the graph, x is greater than 0, and we rotate it 180 degrees, this portion of the function would line up exactly with this portion of the function. So even and odd functions are both symmetric, they're just symmetric in different ways. So we've seen how to tell if a graph is even or odd. We can do the same with equations. If I gave you some equation, f of x is equal to x to the 5th power plus x, how would you find out if this equation is odd or even? All you have to do is plug in negative x for our input and see what output you get. So here we have negative x to the 5th power plus negative x. And we know that if we take a negative number and we take it to the power of some odd number, it's just going to give us another negative number. So this is equal to negative x to the 5th power minus x. Notice how this output is equal to the negative of this output. So f of x is equal to the negative of f of negative x. If we take this output and we multiply it by -1, then we get this output, which is what an odd function does. Let's look at another example. H of x is equal to 2x minus x squared. So what would this function be? Well, let's plug in negative x and see what we get. 2 times negative x minus negative x squared. This would give us negative 2x minus x squared. Notice that this h of negative x does not give us the output that matches with h of x. So we know right off the bat this isn't an even function. Well, is it an odd function? If we take out the negative from this output, then we get negative of 2x plus x squared. This is not equal to the negative of h negative x. It's not equal to it. Notice that h of x is equal to 2x minus x squared. Here we have the negative. So if this function was odd, this term would have to be equal to this term. But it's not. Here we have a positive x squared. Here we have a negative x squared. So in that case, we know it's not even and we know it's not odd. So this function, h of x, is neither odd nor even. Hopefully that's pretty self-explanatory. I don't want to make it any more complicated than it is. If you guys have any questions or any trouble with any of the concepts I've covered in this video, please go ahead and let me know in the comments. I know it's been a really long video. I promised myself I wouldn't make it too long and that I wouldn't drag on for too long, but yet here we are, 30 minutes in. I don't even know how many minutes it's been. I don't know how many minutes this is going to be. Hopefully it's not too crazy. But anyways, I'm going to end it here. I really hope you guys enjoyed it. I know that this stuff, it's really elementary. You guys have probably seen this before. Maybe you haven't, which in that case is great. If you've never seen this before, great. You're learning something new. But this really is the stuff that we need to know in order to get to the more cooler, advanced stuff. So I hope you guys enjoyed it. Please give me any feedback on this video, anything you liked, anything you didn't like, and I'll see you guys in the next one.